Okay, so arrays and collections. We're combining these two chapters together, chapters 8 and 13. Chapter 8 is on arrays specifically, and chapter 13 is on collections. We'll probably go into a number of topics at a high level, as opposed to getting terribly deep. We could teach basically an entire semester course on these two chapters. And if you see in the catalog the data structures class, then that's your opportunity to get more into this. But we just want to introduce how you use these topics in Java and get you started with being able to implement programs using arrays and collections in Java. So the objectives for tonight are, as advertised, arrays. We'll talk about what the common collections are in Java that are available to us. There's a number of interfaces and classes. There's a whole chapter again on interfaces and inheritance. So I'm not going to try to cover all of that tonight, just enough for you to be aware of how to use these things and what they mean when you see the terminology. But in a nutshell, an interface says if you're going to implement a class, here's the basic set of functions that you have to implement, and gets to the detail level of specifying all of the data types on the parameters, the return data types, etc. If it says that you have to have one of these methods implemented, then if you try to create a class and you don't have that implemented, then the compiler is going to complain to you, obviously. What that allows us to do, though, is other code that you might write can always rely on, if you're a class that implements that interface, it can rely on being able to call that function in that way. And there may be a dozen different kinds of classes out there that implement that interface a different way, or you could supply your own implementation. But the fact that they have a common interface that they all support, it's like having a contractor come work on your house, and you've got a contract with them that says, here's what you have to do and here's how much I'm going to pay you, and everything's agreed to up front. So it adds some regularity to the programming. So when I say increase awareness, that's what I'm talking about. I'm not going to give you every nook and cranny of that topic. We're just going to cover enough of it so that you can move forward and be productive. Along with these different collections and things, as computer scientists, hundreds if not thousands of algorithms have been implemented over the years, and a pattern that emerges is you realize, wow, a certain kind of collection that has these traits seems to work better for this kind of an algorithm than the other data structures. I have to go the long way around the barn to implement the same problem with some other data structure. But boy, this particular data structure works really well and it lets me write really clear and efficient code, or targeting some other factor that you're trying to optimize for. A little bit about generics in Java. Again, I just want to introduce that so that you can tell me what it is if need be. Anonymous methods, Lambda functions, these are all in the Stream API. Those last four are sort of all in a category of stuff that didn't exist initially with Java or C# or these kind of languages, but the features were added as the languages evolved to allow us to do some really cool things. I remember the first time when Java and C# came out with these features, and I realized the kind of problems that those were going to make easy. It was like, wow, this is amazing. How did anybody come up with that syntax and think that it would be cool to implement it? I just thought, man, these people are geniuses. But it's very useful if you can learn how to use these techniques. They can be very powerful. Okay, jumping right in. So what we're trying to do here, we're trying to address how we manage data in our programs. You start learning a programming language, and it starts out with the COP 1000 students. They're learning, gather some inputs, do a couple of simple computations, do some print statements, and hopefully do it without crashing, right? That's about the extent of COP 1000. We're trying to introduce a lot of techniques, not trying to get specific about one language. But as we progress into more complicated algorithms, we realize pretty quickly that it's hard to do anything useful if you can't gather a set of data and manage it. If you're trying to write a program that helps you balance your checkbook, you're going to have to gather a bunch of data about the transactions that occurred that month, checks that you wrote, deposits that you made, transfers in and out of the account. You're going to have to collect all those things, organize it, assign attributes to them. What kind of transaction is it? What's the check number on the check? Has it cleared the bank or not yet? Is it still outstanding? All of these different attributes of the data have to be gathered in, stored someplace in memory, and then iterated over or processed in some interesting ways to implement these algorithms. And so we start talking about things like arrays. So an array is the first data structure we talk about because it's one of the earliest ones that existed. I remember back on my first computer, the little TRS-80 Model 1 from Radio Shack that I worked on, that was the only data structure that you had. There weren't any other fancy heap-based collections and classes and all this stuff. It was all very raw and very right there immediate for you to process. And you didn't have very much memory anyway, so it didn't really matter to get that fancy with it. But here are a list of some of the collections we're going to be talking about. And you can see some of the commonalities and differences. Why do I have an array and array list? So these start to beg the question, what is the difference between them? Why would I use one or the other? And what problems are we going to talk about that might be conducive to one of these over the other? So keep that in your mind as we start to talk about and you start to see these different collection names brought up. Okay, so what is an array? And how do I use one in my program? So when you've been declaring variables all along, again, for a couple of semesters now. So for example, this first statement where I declare average score, that's a single double value. I know I can go look up in the table in the Java specification how many bytes a double data type takes up, and it's just one of those. So it's a single variable of type double, and that much memory has been allocated. But if I put the little open brace, close brace, or open bracket, I'll try to use consistent terminology. I usually call the square brackets brackets and the curly ones braces, but it's just a convention. They're both a kind of bracket, both a kind of sets of braces, so it can get a little confusing. But if I declare with the brackets after the data type, I'm declaring an array of that data type. I don't have one yet. All I have is a variable. Now, how much memory is going to be allocated for sales figures? It isn't necessarily related to the size of a double. If I declare an array of integers, or an array of bytes, or an array of doubles, or an array of strings, the size of the variable is going to be the same for all of those because it's essentially a reference to an array. And I haven't actually told it to allocate the array yet. Okay, if I say sales figures equals new double using the new operator, I've created an array of 20 doubles. So now I've allocated 20 times the size of a double, that much memory. And the thing to realize about an array that makes it unique is it's going to be contiguous memory. If a double is, what is it, 6 or 8 bytes? I forget. Somebody refresh my memory. The size of a double. Let's say it's 6 bytes. So I'm going to have 120 bytes of continuous memory all in one block allocated for this. Right? An integer is easier because an integer is 4 bytes. Okay, then I'd have 80 bytes of contiguous memory allocated for this array. And that's important. So there's also, you have to understand the difference between the capitalized data type and the uncapitalized data type. The all lowercase double data type is the intrinsic data type that's built into the language. When you see the capitalization, there is a class called double that somebody has implemented someplace that acts very much like the lowercase intrinsic double data type, except that it usually adds some more helpful functions to it, methods that allow us to do interesting things like parse a string to a double, or all kinds of things. You can look this up in the language specification, Java lang.double, and see what all the methods and properties of double are. So yeah, useful stuff. And it's the same for the other ones, integer versus capital integer has a, integer class that wraps the intrinsic integer data type. If I'm going to use an array, you probably heard this over and over again now with different languages, but elements in Java, like other languages, are zero-based. One of the funny stories about different languages and how they do things is BASIC used to be a one-based index language. It was meant to be very easy and approachable to learn, and when you implemented your code, if you referenced array element 1, you got the first element in the array. If you implemented, so the array indexes went from 1 to the size of the array. However, knowing that people used other programming languages and that they kept having people complain that they were referencing element 0 in the array and getting a subscript out of bounds error, the people that wrote the VB compiler, or interpreter as it were, decided that they would also support element 0. Okay, so that gets really confusing. So if you write your program and you're assuming that the array is 0-based, and you go from 0 to the size of the array minus 1, and somebody else writes in the same language, same computer, and they write theirs based on 1 to the number of elements, not minus 1, are both pieces of code going to work? Yeah, so when you said I want an array of 10 integers, you got 11. You got 0 through 10. That way, whichever way you decided to write your algorithm, all of the subscript values in the array would work, essentially. But instead of getting 10, you got the memory allocated for 11 integers. I guess they thought they were being nice to the programmers, or nice to the students. You get into a lot of situations like that where, no, they're not doing it to be nice to people learning the language. What they're doing it for is backwards compatibility. What they really wanted to do is 0-based, but since in previous generations it had been 1-based, and companies especially had written lots of code assuming it was 1-based, a change like going from 1-based to 0-based would break all of their code. Because anytime they access the 10th integer in the array, they'd get a subscript out of bounds. So software that used to be running last month, we took a Microsoft update, and now our code doesn't run anymore. That doesn't look good in the press. So this was, I'm sure, a concession to the backwards compatibility folks. But anyway, it's an interesting footnote to history about how Visual Basic supported both zero-based and one-based arrays. But no, in Java, we're just zero-based. So you get 10 elements, 0 through the number -1. So you just got to remember that and write all your algorithms accordingly. Now, if you're like me, you'll eventually forget, or you'll accidentally, at 2 in the morning, caffeine-induced stupor, you will forget that. And when you do, when you run your code, you'll get array index out of bounds. That's all it means, is you access something that was out of the allocated number of elements in the array. No big deal. Look for the logic error and fix it. Okay, so another thing in Java, when you have an array, so it allocates this chunk of memory. Let's say I've got 20 integers, so 80 bytes of memory. All it did was it said, okay, I'm going to make a mental note, or well, not mental, I'm going to make a note internally that says that this block of memory has been allocated associated with this name, the name that you gave the variable. It's not going to initialize it because that would take more time. This is another one of those differences between languages. Back when I was at American Airlines and we were trying to decide whether to use Microsoft C++ compiler or Borland C++ compiler, we were analyzing the differences between the two, trying to decide which would be better for us to invest millions of dollars worth of programming time into to develop our product from scratch. And one of the big differences between the two was if you allocated a variable or an array or some other object in Borland, they did not initialize anything for you. You had to explicitly initialize it to what you wanted it initialized to. That allowed their code, as advertised, to be more efficient, because you wouldn't be looking through the code, the assembly that got generated, and see all these initialization steps in there. Microsoft would do that, because from Microsoft's point of view, we get tired of people complaining to us that they had a bug in their code that's blamed on us because we didn't initialize the variable to 0. So two different philosophies, two different implementations of it, and you just have to decide. But having decided, you just have to live with how that particular product works. So we're using Java, so allocating an array does not initialize the elements of the array. So if you want them initialized, you have to write a for loop that initializes them. So you'll see that commonly, as somebody will allocate an array variable, and then you'll see a for loop that says set them all to 0 or something. Multi-dimensional arrays are pretty straightforward. Instead of having just a vector of a bunch of values, you have a table of values. So if I have a two-dimensional array, you have rows and columns visually. What's that going to do in memory, though? If I say I want an array of, let's do a tangible example here. So something like that.
Is that a multi-dimensional array?
That is a multi-dimensional array. 2 in this case, two-dimensional. So it'll be a table of 5 rows and 4 columns in each row. Correct? I mean, you can visualize it any way you want to, but the main point I wanted to make is there's a specific way that, because just like with the one-dimensional array, when I declare and create an array like this, I'm going to get a continuous block of memory that's going to be 4 times 5 times the size of a double in size. And if I try to reference one of those elements, it's going to do some pointer arithmetic to figure out exactly where in that block of memory the double that I'm asking for actually resides in that block. So that's the main thing. But if you write your loop such that it's got 4 columns of 5 rows, Java doesn't care. But if you're looking at it in memory, you kind of need to know, wait, do the rows, does it do all of the first row of 4 first and then the next row of 4? You have to know if you're looking in memory. Very rarely would you ever have to do that unless you're diagnosing some very strange bug. But it's important to know that that's how it works because of some stuff that we'll be talking about later when I compare this to a collection, how it works. So just kind of file that away. Even if it's a multi-dimensional array, it's still a continuous block of memory. It uses all these values, this for the data size and these for the number of entries that it's going to have.
So like there's 5 columns and 4 rows?
Of doubles, yes. So that's how we can definitively decide how much memory that's going to take. Yes, sir.
Is the D supposed to be capitalized or lowercase?
As I said earlier, there are 2 different data types in Java. One the lowercase d and one the uppercase d.
Okay.
The uppercase d is a class that wraps this data type and provides some additional methods in the java.lang namespace. Okay. So here's an example of initializing the array. Java does provide, even though it doesn't do it for us, it provides some interesting syntax that allows it to be convenient. If you don't want to create a loop, you can use the curly braces in an initialization instruction. So this data values 2 line, I mean the data values 1 is just what I illustrated earlier. So I have a variable that indicates that it's probably going to be an array of capital D doubles. However, I don't know how many. No memory has been allocated yet because I don't know how many doubles I'm going to need. So this is just equal to null. Data values 1 is equal to null at this point. I go to the next statement, data values 2, and it has the same problem. I don't have a number of values specified here for it. However, because of the syntax Java provides, it gives me the ability to provide a list of 8 values. It is going to use that as the count. So now I'm going to have 8 times the size of a double bytes of memory allocated, and it's going to use this list of values to initialize them for me. So that's convenient. So instead of doing the equals new approach like this, you can do it the shorthand way if you want to. And then the third example does it the traditional way that I illustrated first, which is I allocate data values 3, I create a set of 20 new double type values, and every one of them, all 20 of them, 0 through 19, are going to be equal to null. Okay, and that's one of the big differences you just need to understand is the value of data values 3, the variable, is now pointing to a block of memory the size of 20 doubles. It's not null anymore. Data values 1 is equal to null. Data values 3 is equal to the memory address of a continuous block of memory someplace. But in that block of memory, all 20, 0 through 19 of those doubles are set to null at this point because they haven't been initialized with anything. Okay? So then this for loop goes through and initializes them, and now they're all set to random doubles. So just 3 different ways of doing a similar thing and getting different results accordingly. And this is a nice illustration down here at the bottom also of how to print. It's just a quick way to print the contents of a array variable. There's an arrays class java.lang.arrays. It might be java.collections.arrays. I forget what the namespace is, but it's a class named arrays, and it has a bunch of helper functions in it, one of them being toString. And if you pass it a variable of type array, it will iterate through that array of values and print them on the screen for you, which is kind of nice. If you're just trying to do a quick and dirty or a classroom project, that's probably all I'm expecting is that kind of output, unless I say otherwise. Lots of neat helper functions for us in Java. So common stuff that we can do with these arrays, we can iterate over them, which means we're going to do some kind of while loop or for loop or something, and we're going to go through it. There's also this thing called an iterator that I want to introduce to you, and we'll start looking at that as we go through. An iterator is another way that we can iterate over the elements of an array or a collection or other things that aren't arrays or collections. But it's a thing. It's a specific class. It's interfaces that support being able to iterate collections of things. I might want to search it. So it may contain a value, if I assigned it to a bunch of random data values like this previous example, maybe the next thing I want to do is ask the user to enter a number, and then I search through the array and see if there's something with that value in the array. It's another thing that I can do. I can search arrays. I could loop through it and say, give me all of the values less than or greater than. I mean, any kind of an operation you can think of. We could get crazy with this, coming up with convoluted problems to implement with respect to collections of values of things. Another common thing that you'll see people do is sort data that's stored in arrays. You'll heard about the bubble sort or the insertion sort or heap sort or quick sort or any number of very common classical sort algorithms. And it's good to start at least recognizing the name of them at this point, and then the next layer of the onion is to implement them. Next layer of the onion is to compare the relative performance and space characteristics of each algorithm, and it just gets deeper and deeper and deeper as you fill your Rolodex with all these different algorithms and data structures that exist throughout your career. But we'll start simple. So let's see if it's possible to quickly implement bubble sort. Let's see, new project, sort stuff. Put on my glasses so I can actually read this. Don't need plugins. Okay, so I got this main function. I'm going to delete all this stuff. Let's use our example from earlier. I'll do it kind of like this. Let's see. We figured out there was a way to increase the size of this. Was it plus? There we go. Double numbers equals new double 10. Sounds good. There we go. So now, with very few keystrokes, I have an array of numbers. And I can print them. What was it saying? Import? Sure. Let's see if this works. I said import it. Okay. Hello and welcome. Oh, I didn't put a carriage return. Let me run it again. Okay, so I created this program and it generated 10 random numbers, and then I printed the array of numbers. Easy cheesy. So now, after printing them, I want to bubble sort them. Okay, so this bubble sort algorithm is pretty simple. It's like one of the first classic sort algorithms you learn. Essentially what we're doing is we're taking a list of values, if you think of them as a column of 10 numbers. Think of it as taking the heaviest one in the list, the largest value, and it sinks to the bottom of the list. So you make one pass through the list and you exchange elements until the one with the highest value becomes the last element in the list. Great, now I know one value is sorted. The last one is the highest one in the list. Then you go through the list again, looking again for the highest one in the first 9, and it falls to the 9th position. You get the 8th highest value and put it in the 8th position, 7th position, 6th position, etc., until you get down to the first element and the second element, and if they're out of order, you swap them, and at that point, you're guaranteed that the whole list is in order. So that's a very common thing, and it's called the bubble sort, or you might hear it called the sink sort, because conceptually, if the heaviest one is falling to the bottom, it's a sink sort. If the lightest one is rising to the top each iteration, then it's a bubble sort. So that's why it's called that. So I need to do an inner loop, but my outer loop is going to be iterating the length minus 1. I know you're just kind of following along, but I'll just try to talk through this as opposed to getting stuck on any one point. And then I'm going to have an inner loop, and I think that it's starting to anticipate what I'm trying to do because of my comment, I'm guessing. But I want to start at I plus 1 and go to the length minus 1. No. Because I'm doing a sink sort, and so I want to go from 0. I always want to start at 0. And there's multiple ways to implement this too, like I said, the sink sort versus the bubble sort. I'm doing a sink sort. Okay, so it anticipates what I'm doing here. It says if the two numbers are out of order, stop it. You're too smart. So what I'm doing here is swapping those two elements that are adjacent to one another. And that's pretty much it for a basic sort. So every time I start at the 0th element, I go down the list, I compare adjacent elements. If they're out of order, I swap them. This is like an algorithm within an algorithm. If I have two variables, A and B, how do I swap them? Method 1 is I have a temp variable, shell game. I put A into the temp variable, I put B into A, I take what I put in the temp variable and put it into B. Now A and B have the opposite values. Okay. After I do this, then I want to print the print the array again. And so hopefully I will see after I run this that my numbers are in sorted order at this point. Fingers crossed. Yeah, they generally look like they're all in order. Yeah, it's the same list of numbers, and in the second one, they're in order. Okay, so at a high level, I picked a problem. I want to create 10 random numbers. I want to sort them, and I want to print them before and after I sort them. That's the problem description. I picked a data structure that was conducive to my problem, an array. So I created an array of 10 doubles and initialized it, printed it. I implemented an algorithm to sort them. I could have extract a method. What are you doing here? So IntelliJ is really cool. If you want to take a block of code and extract it, you can, and it'll create a method for you. So I pass it in a list of numbers and it sorts them for me. This is one of the cool things too about arrays. Because I'm dealing with a block of continuous memory, I can tell this function where that block of memory is, and it has access. It can go through there and manipulate the data at that memory location. And my main function is using the exact same memory. So upon returning, I don't know what you're doing here, but instead of extracted, how about we call it bubble sort? There. All right, so now my main function looks a lot better. I could also extract this into a method. Initialize randomly. And now my main function looks very neat and tidy, doesn't it? I don't want this. I think this is more of that boilerplate, right? So I declare an array of doubles, I initialize it with randoms, I print it, I bubble sort it, and I print it again. Now I've got a very neat and tidy main function with just these 5 lines of code. And I've got 2 functions, initialize randomly and bubble sortie. Okay, so that was an example. Any questions about anything specific on that? Anything that bothered you? I know I went through it really quickly. Hopefully we'll have it on the recording if you want to go back and press pause and review what I did there. But there's nothing secret, nothing fancy. It's just manipulating subscripted elements of this array with an algorithm that sorts them. And like I said, that is the first of literally hundreds of algorithms, if you continue on in programming, that you will be picking a data structure that roughly fits your problem, implementing an algorithm, and then debugging it and trying to get it to work, and then remembering how you did it for the next time you need to pull that out of your tool belt. Okay. So we did a bubble sort. Check one off. Okay, so the next thing is collections. And, you know, we're going to do much more on arrays because that's the main focus of this unit. But like I said, I wanted to introduce all the rest of the stuff to you also. to set you up for things that come after this. So as I said, the memory behind an array is stack-based, kind of. I mean, the way Java does it is, sort of a hybrid, I guess. But classically, arrays are located on the stack. Now, one thing I want to say about using this terminology stack is it'll become more clear later. Often programming students get confused when I use the word stack in this context because there's the stack and there's the heap. When you allocate local variables inside your code, they go on the stack. The stack is a block of continuous memory that is allocated at runtime at the start of your program, and that's where, as the program is running, local variables, function parameters, when you call a function, it puts the address where to come back to on the stack. That way, when you call the function and you run all the code in the function and you hit a return statement or you hit the closing brace on that function, it says, oh, where am I supposed to go back to? It looks in the stack at that memory address and says, oh, okay, and does a go to or branch statement back to that location and continues in the calling function. Okay, so all of these different things are being used while your program is running, using that data in this contiguous block of memory called the stack. It's confusing when we get to very soon, and then you hear stack used as the name of a collection or a name of a data structure. It's like, well, wait a minute, you just told me the stack was this thing that was used for parameters and local variables. It's reverse. There's this data structure called a stack and a queue and a list and a map and all these other things. And when they had to pick a data structure to solve the problem of managing local variables and parameters, they said, you know what? The best data structure to use for that would be a stack. So they did. They used a stack data structure to manage all that data, and then it just got labeled the stack. Okay, so if it's the stack, it's talking about the one big blob of physical memory. If it's a stack, we're talking about the data structure that implements the behavior of a stack. So that's what we're talking about here. So when I say that this array is stack-based, it's allocated similar to a local variable classically, where you have this blob of contiguous memory on the stack that's set aside while that function is running, while that variable is in scope, that's using that block of memory for its work, okay? In Java, since we're using the new function, the new operator, anytime you see the new operator, the memory for that's coming from the heap. So it's a continuous blob of memory. It just happens to be allocated out there in the heap. An array can hold these intrinsic int and double data types. Collections can't. Collections, you have to use an object. And here's where we're going to start getting into the differences between array and collections, and this collection versus that collection. So in general, these collections we're talking about are going to be heaped based. And I've mentioned before loosely the garbage collection. One of the great things about Java and C# and languages like that, as opposed to C++, is that we don't have to keep track of all the memory we've allocated and make sure that we deallocate it when we're done with it. In garbage collected languages like Java and C#, the garbage collector process running behind the scenes will go through there and look to see what you're not using anymore and reclaim it. So we don't have to worry about that. Not with arrays, but yes, with collections, that's true. Yeah, and there's a few basic interfaces. Again, you can read about this in chapter 13 in more detail and more precisely. I saw something as I was preparing for this lecture that was talking about a common interview question is diagram the relationship between the hierarchy of all of the collection interfaces and the classes that are implemented within each one of them. I'm like, if anybody ever asked me that in an interview, I'd say, sure, can you give me access to the Java language specifications? Because I don't remember stuff like that on purpose when I can go look it up someplace. So, but yeah. Okay, this list interface. So I mentioned earlier that an interface is simply like a contract. You create an interface, which is a contract that says any class that purports to implement this interface has to follow these rules. It has to abide by this contract. It has to implement all of the functions that are implemented here. If it doesn't, it's abstract. It's still abstract. We can't actually use it yet. We can't use an abstract object because it isn't following the rules yet. Once that class implements all of the required methods in the interface, then it's concrete, it's not abstract anymore, and then we can create one of them. So a list, a lot of this is just, facts that you have to remember. I hate to just throw out dry facts like this with no application, but a list is an ordered sequence of objects. You can insert them. This is another difference between, I think I reference this again later in the presentation, but since all of the memory is allocated at once with an array, can I increase its size? Can I decrease its size while I'm using that block of memory? No, that's going to be very difficult. We specifically call that a buffer overrun. You're not supposed to do that. Like if I allocate 10 doubles and then I access the 11th one, Java's going to complain and say, no, a subscript out of bounds. You can't do that. You don't have an 11th one. You only have 10. Yeah, so don't do that. There's nothing I can say where I can say, hey, by the way, here's this array. Java, can you allocate 5 more so now I have 15 instead of 10? No, because it was already a pre-allocated blob of memory of a specific size calculated based on the data type and how many of those you told me you needed. So no, I can't change the size of it. Yeah.
So we can append more things into the...
There is an append operation. However, that's collection based. And if you try to do that in an array, all that means is I've got some logical notion of how many of the elements I've already used. And append would say, yeah, go to the next one that I haven't used yet and use it. But where do you store which ones you've already used yet? When you declare an array object, you're using all of them. Even if they're only initialized to null, you're given the entire budget of values, entries, and they're all initialized to null right then when you declare that. When you say new double 20, right then it gives you that blob of memory with 20, size enough for 20 of them. So there is no such thing as append. What would append mean with an array, right? Now, if I have a collection, I can, because the collection is out here in the heap, and I can say things like, well, I want another one of those appended out here to the end, like a linked list. A linked list happens to implement the list interface. So there would be an append, there would be an insert at, there would be a remove at, right? Because it's like removing or adding a link in the chain, right? Those operations all exist and they make perfect sense with a list, but not with an array. And this implementation hiding concept is very important to grasp. When you start thinking abstractly about these collections as abstract interface implementing things, then do I care how they happen to implement the append method? No, I don't. Not directly. All I care is initially that, hey, I'm trying to implement this sort algorithm and I need the append operation to do what I expect it to do. I don't care how they implemented it, unless your teacher is telling you to implement the append method, or some made up scenario like that. So then there's this array list class. Okay, well now we've just talked about all the differences between an array and a list, and now we're going to talk about the array list class. So this one is a class that acts like it's an array, but it has all of these methods available to it, which what does that tell you? Behind the scenes, it ain't really an array. It's just a heap allocated object or set of objects that's pretending to be an array so that you can use it with the simple syntax with which I can use an array. However, I don't sacrifice being able to use all of these things. And you might think, well, if I've got this, why would I ever go back to using an array? Excellent question. Because it's the classic way, it's the primitive way, it's the first way that every programming language had to start with before anybody sat down and implemented all of these fancy classes and extensions and other data structures on top of it for their computer science class. Yeah, a whole bunch of useful stuff. If I was going to be implementing something, I would not use an array. I would use an array list to start with because it has all these very useful methods in it. Is empty. Hey, here's the value 12. Can you tell me the index of 12 within the array? I don't have to write my own search algorithm and loop through the elements of the list. I can just say, tell me what the index of the value 12 is inside this array list. And it searches it. Somebody already implemented the search algorithm. So, yeah, very interesting. We get to these iterator objects. And so suffice it for now just to let me introduce the topic of iterator, to say iterator is another abstract, easier way to iterate over the elements of some collection without doing it in such a way that's specific to arrays or specific to linked list or specific to something else. It gives us the ability to create an iterator. If I had to describe generically how to support iterating the elements of a group of stuff, could I define an interface that says how that's supposed to work so that the people building the array list class and the linked list class and the hash map class and all these other classes can implement that interface and adhere to the contract and give all the programmers out there a common way to write their code to iterate over those objects. And so that's what they did with these iterator class interfaces. You basically can say, hey, here's this array list object. Give me an iterator over it. So now you have an iterator object. You can say, give me the first element in the list, and then give me the next item, and next item, and next item, kind of like next random works. So just suffice it right now to know that there is a way to iterate these things generically that basically works no matter what the collection is, because it's implemented differently for each one of them. And then lambdas and predicates, those are all pretty cool too. Like I said, how big of a cure for insomnia do you want me to create with this lecture? You know, because I can go deep and talk about all kinds of esoteric things dealing with the language and other languages in general, but suffice it to say I'm introducing these topics and the rabbit hole goes deep from here. Okay, example of the iterator is I've got this items thing. In this case, let's say that it's an array list. Okay, items is an array list. So I can say, hey, items, give me an iterator. And somebody implemented the iterator class, and they're going to be able to return me an iterator object. In this case, I can guess, because of this thing here in the less than greater than, it's using generics, that this items is an array list of strings. So this is how you would loop through all the elements of an array list of strings, is you would say, does it have any elements? Is there a has next? If it returns true, then you can say .next, get the next one in the list. And in this case, remember how we were talking about it with an array, there's no way to know how to append because where's the next place? Well, this iterator is an object that remembers. It's like you created an index finger and you stuck it on a place in the collection. And so when you say next, it says, okay, well, this is where my finger is. So move the finger to the next one in the list and return that one. So that's what the iterator does basically. With every kind of collection for which the iterator is implemented, that's what it does in whatever way it needs to for however that collection was implemented. And if you know nothing other than this example here, you should basically be able to apply that to no matter what collection we're talking about, because the iterator is going to work the same in every collection. With maybe a few caveats here and there specific and what as makes sense with that particular collection. But this loop would basically work no matter what kind of items you're working with here. So pretty cool. Generics is a thing that is a feature of the Java language, like it is with other languages, C#, Visual Basic.NET, etc. Did you know that they actually, when they came out with .NET, they were creating all these languages. They created a COBOL.NET. It's really amazing what clever people can come up with when they put their mind to it. And, some new abstraction comes along, like the .NET Common Language Runtime. They said, oh, wow, we could implement that against COBOL. And there was something, I think they were talking about creating a Java.NET at one time back in the late 90s. But they ran into, Microsoft was in the middle of that antitrust legal battle at the time, and they didn't want to throw any gasoline on the fire. There was actually a language there for a couple of years called JSharp.NET, which was, I think, the closest they felt comfortable coming to creating a Java.NET, which would have just been too brazen, and there would have been pitchforks and bonfires in the streets and things like that if they'd have done that. But yeah, a lot of these concepts come from that time. Java implemented them in a fashion, C#, .NET languages implemented it in a fashion, and you'll see them, so when I say generics, I could be talking about any of a number of different languages, and the concept is the same. So my hope is if you figure out how to do this in Java, you can apply that to any other of this class of language. If I had to give a name to the class of language, I'd say, compiled languages that have a common runtime framework, like Java has the Java runtime environment. .NET languages have the common language runtime. They're conceptually kind of the same specification, or they represent the same, place on the map. Anyway, so generics. So sometimes you need to implement something where you don't care what the kind of object is. The contract to do that, like this iterator that we saw, the contract's going to work the same regardless. And I want to be able to implement those things and support all of the existing data types. I mean, literally down to the lines of code that I use to implement that function are going to be exactly the same if all you did is a global find and replace on the type from string to integer or from integer to double. All of the lines of code are going to be the same. So then why do I have to copy and paste that function 8, 9, 20, 50 times so that it's supported with each of these data types? I shouldn't have to do that. So they wrote the language where I don't. I can write a set of instructions and refer to the data type generically, and that's what you saw on that previous example inside the less than greater than. This iterator class was written to support generically any kind of type. In this case, I'm using it to iterate a list of strings. So that's what generics is. Yeah. And I'm hoping that that introduces the generics topic and I don't have to get into any other stuff. The reason why we're doing this is we want to promote type safety. So we want to be able to write an algorithm and make it work without caring what the data type is, and at the same time allow you to use that in a way that's, so what people got doing is they would write code using void as the data type. Well, you can do things to a void that you can't do to the specific data type, and it made it to where there were all kinds of bugs going around. And when they came out with generics, it just got rid of all that stuff and let people write much more concrete code based on it. So it's much better. So here's an example. If I wanted to create a list, notice the syntax here. I'm using the name list on the left. So this is, you would read this as, I'm declaring a list of customer objects, the variable name customers, equals new, the new operator, I'm going to create it. But on the right side, I switch to array list. And there's a very specific reason for this. List is the interface. Array list is the class that implements that interface. And again, the customer inside the less than greater than is using generics. So this is an array list of customer objects. And caveat here is, if you're going to do this, there's requirements on the object, the data type that you put in there. The data type that you use must implement the interfaces required for the array list to do its job. And in this case, it's comparable. Comparable is the name of the interface. So if I was implementing a customer class, it'd say class customer, and then I'm going to have to say implements comparable in the syntax that's required there. We have a chapter coming up on, again, interfaces and inheritance, and you're welcome to dig more into that if you want to go down that rabbit hole. But I'm just trying to introduce it so you recognize the syntax when you see it now. You'll also see at some point, look up the difference between comparator and comparable. That's another common interview question for Java candidates. So write that down, go Google comparable versus comparator in Java, and convince yourself that you understand what the difference in those is before you move on and forget about it. Yeah, so another thing when we talk about comparable and comparator, so the fact that the array list you can have those things sorted, we have to talk about natural sort versus using an implementation of a sort method. Okay, so when we implement this comparable interface, we have to implement the compare method inside there. So you have these two instances of a customer object. Which one is greater than, which one is less than? Well, I don't know. I assume we're not going to use the memory addresses of them. That wouldn't make any sense. Are we going to use the customer ID, and whichever one has the newer customer ID is the greater one? How does that work? So when you implement that customer class and you override the compare method, you get to implement what less than and greater than mean. And the way that compare method works is if you return 0, they're equal, logically equal to one another. You have implemented it to determine that they're logically equal. If you return a negative number, it's less than. If you return a positive number, it's greater than. The next one we'll throw out there is linked list. Again, apologies for all of the dry just list of encyclopedic information here with little application. The linked list class is like the chain. You know, they call it linked list because it's like a chain of links in a chain link fence, or, you know, in a log chain. Each element in the list has a data member in it that points to or references the next item in the list. And the last item in the list is typically null. Often this is implemented as a doubly linked list, so it wouldn't just have one, which we would call a forward linked list, it would have two. It would have one pointing to the next element in the list and one pointing to the previous element in the list. And as you might guess, the first element in the list, the previous element, is null. The last element in the list, the next element, is null. And that indicates where the chain ends. Of course, there's other implementations where you can have a round, you know, continuous one, where you add one element to the list, it points to itself in both directions. You add a second one, they both point to each other in each direction, and that way it's always a continuous loop. And then where is the beginning, where is the end? There is none, logically. It's just a continuous list. And you can traverse it with an iterator object, just like the previous example. The next collections we're going to talk about are a stack and a queue. I talk about them together because they're such nice contrast with each other. You know, stack, you can visualize that like a stack of pancakes. Or another one is, you know, when they have those stacks of plates and the little springy machines at Golden Corral, you know, you can set the clean plates on top of it and they all squish down. And if you're going to go get the next plate off of it, you always get the top plate off the top of the stack, right? That's why they call it a stack. The last added pancake is the first one eaten. The last plate added is the first plate taken away. A queue is the opposite of that. You know, if you're standing in line, you get in line, hey, no cuts, right? Everybody has to queue up at the end, and the first one that gets in line gets to be the first one serviced, right? The DQ or deck, or however you want to pronounce that, is kind of like an odd little permutation that came along. It's essentially a double-ended queue. And it's similar to the array list. You know, we have this array. Why do we need an array list? An array list is an array, but supports all these useful things that I want it to anyway. Same thing here. A queue is only one way, but somebody came along and said, no, I don't want to be restricted to that. I also want to be able to take things off of either end of the list. There's interesting examples for using all of these, the applications for them. I mean, there's an infinite number of applications for data structures like this, but think of like a post office where, or a messaging system, like the event system in Windows, all of the mouse events that are coming in and getting distributed to all the different windows. But if you have a message come in, it needs to be the first one that goes out. But sometimes you put a message on there and it's like, oh no, this is timed out, I don't need it anymore, and you want to take it back off it again. So if you could have a two-ended queue where every time you go to get the next one off of there, you check and peek at the end of the queue and say, oh no, these messages out here are older than a minute. Let's say a minute is our timeout. So let me delete all the ones off of the end until I get to some that are not a minute old yet. Okay, so I've timed out all of those messages, then I pull the first one off the list. I mean, it'd be kind of like going to a line at the bank and shooting everyone that's been in line longer than a minute, right? You wouldn't do that, but in some certain applications, it makes sense. Anyway, yeah, like I said, I can contrive any number of scenarios that might artificially make sense, but this is what we do as system analysts, as programmers, is we think of these problems and then we come up with the data structure that makes the most sense to use for that kind of a problem. Okay, so jumping to lambda expressions. Another thing that became useful, it occurred to somebody that, you know, every time I want to write an algorithm, like those extracted methods, I have to create a function. So I have to stop. I have to think of a name for the function. I have to define what the parameters of the function are. It's all this boilerplate. And then I got to put it in a source file, myfunctions.java, and then I have to store it somewhere. Then I have to compile it and organize the modules. And there's just a lot of crud that goes into creating this function that I'm going to use in one place, and it's going to sit there forever in my code base and start collecting dust, and eventually it's going to be obsolete and somebody's going to have to remember to go clean it up. Lots of technical debt related factors that go into this. When it occurred to somebody, well, why do I have to do all that? Why do I have to give it a name? Why can't I just say, abstractly think of a scenario where I have two values, A and B, and I want to, on A and B, whatever they are, generically, abstractly, I want to calculate the difference between the length of A and the length of B. Now in this scenario, A and B, whatever data type those two things are, they both have to have a dot length member, method, dot length. If they don't, Java's not going to be able to compile it. But if they do, what if I could just create a generic anonymous method right here in line in my program without having to stop and create all of that overhead and that boilerplate and potential later technical debt? And you know, the geniuses that work on compilers and things like that came up with this syntax that fits nicely into Java, into C#, into these other languages that is just beautiful, I think. So if I want to sort this my collection, whatever it is, again, whatever it is it an array list? Is it a hash map? Is it whatever? As long as it supports the dot sort method, which pretty much comparable, if you implement the comparable interface, this will work with it. So anything that supports comparable, you can sort with this line of code and you don't have to have any other functions or anything. It's just beautiful. And I get to sort it the way I want it to. Like here, I'm sorting it based on the difference between the length. So if I had, let's say my example before, say I have an array list of strings. Let's say they're all last names. This line of code and nothing else required would sort that array list of strings based on the length of the last name. It's beautiful. Without any functions or anything. It's amazing. So that's what lambda expressions give you. This A and B in parentheses, that syntax is called a lambda expression, okay? So when you see that word lambda expressions, that's what we're referring it to. You can probably do quite a bit of programming in Java effectively without having to understand what lambda expressions are or use them in any way, shape, or form. However, if you learn how to use these things, you can write some pretty darn elegant Java code that has some really good benefits, like I said, with these not esoteric, but sometimes subtle technical debt implications to them. Okay, so dot sort, dot for each, same thing. If I wanted to iterate over them, this next example goes through that list of strings and modifies each element in the list, trimming, let's say that there's extra spaces after the last name because of the way the data was input. I can go through that entire list of strings in one statement and get rid of all of those extra spaces. Pretty powerful. And again, thinking of this dot for each as a syntax with which I can iterate over a generic list of things, that's pretty darn powerful to be able to write all the in one statement. So again, don't have to know it, but if you do know it, you can do some pretty interesting stuff in Java and other languages that support Lambda expressions. Okay, this last example down here at the bottom is interesting. So it says it sorts a bunch of positive integers where the odd numbers were descending and the even numbers were ascending. Why would you ever want to do that? But the fact that I can do it all in one line of code is pretty amazing. So all I'm doing is I'm basically saying if the number is even, if the, divide by 2, if the modulus is 0, that means it's even, then I want to return A, otherwise I want to return negative A. Same thing for B, and then I subtract the 2. So that tells me, that's my comparison operator, and I'll leave it to you to prove to yourself that that works to do what it says that it's doing. I played with it quite a while preparing for this to come up with something that was weird enough, but yet I could implement in one line of code. So anyway, enjoy. And I mean, if you want evidence that I'm a programming nerd, that's your evidence right there. Okay, the Stream API is another one of these little interesting things. I think of this as LINQ in C#, but LINQ is a better, I think one of the things is two possibilities. It was either invented by the .NET people and integrates better into LINQ in C#, and the Java people came along and they said, well, we're not going to rip apart our language and shoehorn this thing in there just because C# does it. So they provided a form of it, but it just is implemented better in C#. Or the Java people did it first and did it the way they wanted to, and the C# people came along and said, well, we can steal that and then we can improve on it too. So either way, the implementation of the Stream API seems to be a little bit better in C# than it is in Java. And one aspect of that is it's deeply integrated into the language in C# and not so much in Java, but you can still do it in Java. We also refer to this, if you heard anybody talk about functional programming, this is an example of functional programming. It's also referred to as like chaining. So we chain operation. If I have a collection of integers and I want to get just the even numbers, I can say, well, take numbers and stream those values for me. So it's going to iterate over them in a stream of values. Then while you're streaming them, filter out any of them that don't meet this criteria. And then once you've done that, produce a list of what's left over at the end and return that. And that's what gets returned and is in even numbers. But the cool thing about it, the reason why they call it a Stream API, is when you execute this line of code, mostly nothing happens. I mean, some stuff happens behind the scenes to prepare for it, but it's very, very fast. I mean, almost instantaneous, to a point where you're thinking, wait, did it actually do what I wanted it to do? But when it actually does the work is when you start iterating over these even numbers. And then that's when you see the beauty of it streaming through them. Because then it's doing it like an iterator. It says, does it have a next one? Okay, get me the next one. And that's when it goes boop, 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 and it iterates over them just in time when it needs to go get the next one. Which, okay, maybe you could argue that that algorithm is going to take just as long to process the whole list as it would to do it not this weird way. However, in a lot of cases, in a lot of problems, you want the code to look like it's responsive while it's doing the processing. And that's what this produces. There are a lot of places like in Windows where, if you had to click on 8 buttons and then it does all of those 8 operations, that would be very frustrating. What you want it to do is you want it to be processing on the elements as it's coming in as a stream. And that's what the Stream API gives you, is the ability to more interactively process the elements according to the code that you wrote. So, another cool feature. Here's another example again. So let's say that I want to generate a list of 100 numbers. Let's say it was 1,000. Let's say it was 10,000 random numbers. This is essentially, it starts out being an infinite list. Like if I deleted this .limit 20, that would be an infinite loop generating random numbers and then printing them. Generate a next one, print them. Generate a next one, print them. But the limit 20 in the middle there says keep a counter, and when that counter gets to the 20th one, stop. Indicate that there are no more. Like if you hit end of file or something is what it's simulating. So pretty cool. And like I said, there's lots of cleverness to be discovered here. It's all so beautiful and so elegant. It's like Elon Musk trying to describe to you all the things that they've improved on the Raptor engine, right? Unless you knew what it was like before and you had to deal with it and maintain it and fix it when it broke, it's hard to appreciate it when you just see the most recent version. And I've had to do so much of these coding problems the hard way over the years that when I realize the syntax and realize the subtle ways that it improves the way to solve these problems, it's just amazing. I wish you could get that feeling. Okay. I mentioned earlier the idea that you're going to go sit for an interview at some point for a job where this company uses Java predominantly. And one of the things I wanted to go over briefly before we finish this is some of the kind of concepts and questions that you're going to be asked. You'll often be asked, hey, what's the difference between an array and a collection? Just to see if you have had data structures, have you looked into this at all? And so when asked, this is kind of how you'll approach that. An array is fixed size. Once we tell it we have 5 rows and 4 columns, we're done. Until we delete that collection and create a new one of a different size, that's it. Versus collections can be dynamic. They can start out empty. I can append, and it can grow and shrink. I can remove. It's a dynamic size. Arrays use stack. Collections use the heap. Contiguous memory, the reason why you might want to use that in some scenarios is because you can get high performance out of it. The reason why, I'll let you prove it to yourself whether this is true or not, but the reason why you can eke more performance out of an array in the contiguous memory is finding the element you're looking for is arithmetic. You can say multiply the row times the number of row items in each column plus the column number, and boom, there's the memory address of the item that I'm looking for. It's very fast. As opposed to if you have a linked list and you want to access the 18th element in it, you have to start at the head and go next 18 times to find the 18th item. So that disconnection in the memory allocation of all the elements in the collection can make it less performant. Now you've got, hashed collections that address that and become more preferred sometimes than arrays because they have the performance benefits without the functional algorithmic detriments of arrays. So the other thing about arrays, they have to be the same data type. Like I can't have 3 integers, then a double, then a couple of strings, then a byte, you know, because I have to know the size of the elements that I'm working with in order to calculate the size of that memory. That means the elements in the array have to be homogeneous. However, in a collection, well, they can be homogeneous if you want them to be, but you also have the flexibility to make them different types. List, set, and map, well, there's a difference between them. So as opposed to here, we're talking about generically, we're talking about these in the abstract, array type collections and collection type collections. We're talking about the interfaces, the concept. The next question is, what's the difference between a list, a set, and a map? We're talking more concretely now. These are specifically differentiated by their implementation, okay, and what they support and what they don't. So it's very important to know this because this will govern which one of these you use for different kinds of problems. A list is still something you can access if you know the nth element you're looking for. If I know that I'm looking for the 17th element in this list, you can use that subscript, that index value, to directly go get the item you're looking for. Array list, linked list, vector, and stack all support being able to do that. If you know need the nth element, you can go get it. That is defined and supported with these collections. Okay? Set is not like that. Set is just it's non-index sequence. So if you have 2 things, you put the first one in the set, and then you put the second one in the set, they could go in there in the reverse order. They could go in the order that you put them in, because the order, the index of an element in the set is not defined. Duplicates. So in an array or in a list, you can have duplicates because nothing cares about it. They're indexed by the number, right? The index value, not by the value of the element. So you can have duplicates. In a set, you can't have duplicates because they're identified, they're placed in there based on the key, the notion of a key or the value of the element, which means you can't have multiple with the same value or the same key for that value, okay? Map is very similar to set, except that map, if you've ever worked with a dictionary before, map is defined as a key value pair. So I locate an element by its key, but the value is different than what the key is. So if somebody's phone number leads me to their first and last name, is what we're talking about there. The phone number would be the key, and the first and last name, or the object that defines those, like the customer object, would be the value. Okay? So conceptually, that's what we're talking about here is the difference. There's this thing called dot equals, which is very integral to implementing these collections. You have to implement the dot equals method for any objects that you want to be putting in these collection types. And so the question is, if I have 2 objects, let's say 2 customer objects, and I'm going to compare the 2 of them, what am I comparing? How do I tell whether they're equal to one another or not? What does that even mean? I have to define that. I can't just assume it like I can with integers, with all the kind of problems that we've dealt with up to this point, right? We're dealing with simple values like Jones and Smith. Well, Jones is less than Smith because they're alphabetically, I can sort them alphabetically. 12 is less than 17 because, again, numerically there's a natural sort order there. But for 2 objects, 2 customer objects, I could get the memory address where they're located in memory, but that seems really random and not useful, right? That wouldn't help me. that might help me to identify whether they're unique, different objects or not. But in terms of logically solving a problem based on what their memory address is, it's not very useful. But if I define a key, so if I've got a customer object, what might be the key value for a customer object? Maybe customer ID? I mean, I don't know. It depends on what you know about the customer. If you know their first and last name, maybe last name comma first name is a good value for the key. But you could have duplicates there, right? You could have two, Joe Smith. You could have, duplicates if you use that kind of a value. And that's a real thing, like the example here points out. If you're trying to maintain, a database of customers, it's very possible that that customer moved across town, and the last time they did business with you, they had a different address than they do now. And so, do you edit the existing customer object, or do you add a new one with their new information so you don't lose the old information? There might be use cases for both, but you have to decide which one of those is appropriate. The last example here is probably a more useful one, and so that's more common, is if you have an object and you want to know whether it's equal to another instance of that object, you implement the dot equals and you do a field by field comparison. Is the name the same? Is the first name the same? Is the middle initial the same? Is the phone number the same? Right? You go field by field, and if all of those things return true, then the two objects are equal, logically equal. Even if they're stored at different locations in memory, they're logically equal if all of the fields match. So it's up to you to implement that. The dot equals method has to be implemented by you in order to provide a meaningful comparison between the two objects. Java has an expectation if you want your code to work right. And when I say that, your code, if you want how you use these collection implementations, array list, hash map, etc., if you want those to work properly as they were written, then when you implement the dot equals method on your customer object, you have to support certain properties. It has to be reflexive. And again, you have to look up what these terms mean in order to, and they pretty much make sense if you think about it logically. Has to be reflexive. What that means is if I call the dot equals on the same object twice, I have to get the same answer. I can't get true one time and then the next time I do it, I get false, right? For the same object, I have to be able to get the same answer. It always has to say A equals A, right? Symmetric. So if I say A is equal to B is true, then B is equal to A must also be true. That's reflexive. Transitive is the extension of that. If A is equal to B and B is equal to C, then A had better be equal to C, and vice versa. So that's transitive. And then consistent. What was consistent again? I forget. Somebody remind me what consistent is, if you can Google that real quick. What was it? It's not reflexive. Oh, I think what it means is, if I call dot equals on A, and I get, if I call dot equals on A and B, and it says yes, they're true, and some time passes, I can't call it again and have it say it's false when nothing has changed. It has to be consistent. Like it can't be, oh, well, now it's Thursday, so now they're not equal, right? It has to be consistent over time. So I think that's what it meant, if I remember right. And another tool that we have that's related to the same problem is the hash code. So you will be asked in an interview at some point, what is a hash code? And why is it important? So one of the things about, so people like the performance of arrays, but they like the flexibility of collections. So You know, the wizards of computer science came up with a collection that uses hash codes to identify the elements, which allows them to implement it in such a way that you get much of the performance benefit of arrays. That's why we do hash codes. So a hash code is just a number, you know, like an integer that is generated to represent this object. Now if your customer number is an integer, you could use customer number. You can create it however you want to, but it has to be, you know, like with the dot equals, it has to have certain properties. But the reason why it works, the reason why, like I said, arrays are so performant is because when you want to access one of the elements in the array, you can simply do index and memory address arithmetic to get to where that is stored. It's instantly fast, you know, one clock cycle fast to get to that element. So accessing it is very fast. Same with hash codes. If you have assigned a hash code to this object, then finding it again in the collection has been implemented to be blazingly fast. You're doing a similar thing. You're using pointer arithmetic to get to it. A way to visualize this algorithm as if you've been to a conference or a concert and you had to go to will call to pick up the tickets you ordered ahead of time, and you go up to them and there's this table and there's like 20 people at this table, and each one of them has this big box in front of them full of folders with people's tickets in them, and you go up there and it's got little letters on signs on the front of the desk, you know, and I'm Snyder, so I would look for the table that has S on it, and I would walk up to that table and I would tell them my name, and they would look through their little box of S's and they would find my folder and give me my tickets. That's pretty much the way this hashing stuff works, is you have an array list of hash code ranges, and if you have a customer and you're trying to find where that object goes in the list, in the collection, or you have the key to it and you're trying to find that particular object so you can get it out and manipulate it, then all you have to know is the hash code, and you can, of all of those bins, you can jump to the one bin that then has another collection inside it that you can iterate over to find your object exactly. And that's the way hash codes work. The more hash codes you have, the more spread out it is, and the more directly you can get to the item that you want. Now, if you have a customer object and you say, okay, well, hash code, every time you ask me what the hash code of this customer object is, I'm always going to return 17 for every customer object, no matter what the name, what the address, what the phone number, no matter what the object is, I'm always going to return the value 17 for the hash code. It will work, but you're defeating the purpose and you're losing all the performance benefits, because that first table that everybody's going to go to is going to be the same table. All the other tables are going to be sitting there with empty boxes, and you've stuffed all the concert tickets into this one person's box. So every person comes up to that one table and has to then wait in line sequentially to get their concert tickets. The beauty of this is we have a way of creating the hash code that is distributed evenly as possible across all those tables. Even using some algorithm like, let's take the first letter of the last name. Well, that's not going to be distributed evenly, is it? Because there's a lot more B's, let's say, than there are names that start with an X, right? So the person sitting down there at the X table is going to be asleep because then nobody ever comes to their table. We want some algorithm to, no matter what value I give it, it distributes them consistently, deterministically, and quickly and evenly spread across the whole range of hash codes. And so when you look into how to generate a hash code, that's what you're going to find is algorithms that generate well-distributed values across a range But when you have the same object, you get the same hash code every time you call that hash code function. So, there you go. That's hash codes and why we care. So that wraps up all of this generic stuff talking about collections, arrays and collections, chapters 8, chapter 13. As advertised, we talked about common collections in Java. You have a little bit more of an awareness, hopefully, of interfaces and inheritance of these objects, even though it was in encyclopedic form. Throwing mud on the wall, see what sticks kind of thing. Some of these algorithms, we implemented a bubble sort. Again, generic, synonymous, Lambda function, Stream API, those are roughly related topics, and that there are fancy features that you don't have to learn, but if you do learn them, they make a big difference in your effectiveness as a programmer. And then we talked about some questions that might arise during an interview.